Hello everyone, I'm Wenzhang Yang. In this video, I will present our paper Rust-lancet Automated Ownership Rule Violation Fixing with Behavior Preservation. This is a joint work with authors from University of Science and Technology of China and Penn State. Rust is a young programming language for safety-critical software. It's designed to provide both memory safety and runtime performance. Rust conducts static checks in compile time. According to Stack Overflow service, Rust has been the most loved programming language for 8 years in a row since 2016. Rust has already been adopted to build many safety-critical software systems. Rust's safety mechanism centers around two important concepts: ownership and lifetime. The basic rule only allows a value to have one and only one owner. A value is dropped when its owner's lifetime ends. Here, a full value is created and its owner is variable out, and the lifetime of variable out is the whole function. When the function is finished, variable out will free its value automatically. To improve the fixability of coding in Rust, Rust extends its basic rule to have multiple extended rules. First, Rust allows the value's ownership to be moved to a different owner. However, it does not allow any access to the previous owner after the move. For example, in this line, the value in variable out1 is moved to in1. After that, we cannot use out1 again. Second, Rust allows to temporarily borrow a variable's ownership using a reference. A reference can be immutable for read-only accesses, or mutable for read and write accesses. Rust allows multiple immutable references to a variable to exist at the same time, but it only permits at most one mutable reference to a variable at any time. All these rules are checked statically during compilation. They essentially prohibit heavy mutability and aliasing at the same time. Unfortunately, Rust's safety mechanism brings programming challenges to its programmers, confirmed by a previous study. Here is a motivating example. In function moveout, the parameter val is a struct, contains a vector, which can be accessed by val.0. In the function body, val.0 is moved, according a method call, even if this variable is not passed to method into iter explicitly. Then val.0 cannot be accessed anymore. For this case, Rust compilers suggest that you can clone the value and consume it. But the patch given by Rust compiler does not help, since clone changes semantics and increases memory usage. So, can we improve Rust programmability by automatically fixing compilation errors? Here are some limitations of existing techniques. Automated program repair techniques are designed to mainly for bugs in C, C++, Java programs. They are unaware of Rust's unique safety rules. The Rust compiler provides direct feedback for programmers, but sufficient information is not always provided, and fixing strategies or patches are not always provided. Thus, no techniques are needed for Rust compiler errors. We propose our tool Rust-lancet. It automatically fixes ownership rule violations. Rust-lancet has 3 fixing strategies considering Rust safety mechanism and validation for semantic preservation. Furthermore, we evaluate Rust-lancet with 116 safety rule violations from 2 sources. The experiments show its fixing capability of the baseline techniques. Rust-lancet will not generate any wrong patches. Rust-lancet has 3 strategies and a patch assessment component. Before fixing, Rust-lancet converts the input program into an intermediate representation, INF. Next, Rust-lancet starts a fixing loop. Rust-lancet has 3 fixing strategies. In each fixing strategy, Rust-lancet will try to generate a patch. If the patched code is compilable and preserves the original semantics, then Rust-lancet concludes the fixing process. If not, Rust-lancet will try next strategy until reach the loop up bound. Next, I will use the previous example to demonstrate how each step works. Before fixing, Rust-lancet converts Rust program into administrative normal forms. In AF, all arguments to a function must be a simple constant or variable. For the example, here is the original chain call, and here is the corresponding NF code. NF introduces 2 temporary variables to separate the continuous chain call. The first strategy is owner lookup. This strategy tries to replace the use of an older owner with a new owner. For the example, val.0 is moved to temp0, but val.0 is used after move. Owner lookup tries to replace val.0 with temp0 to solve this violation. But the Rust compiler says the code is still uncompilable. Then Rust-lancet starts to try next strategy. Reorder aims to resolve the coexisting of 2 multiple references to the same object. Reorder is also valid for use after move error. For the example, temp0 is moved to function intuiter in this line. Then we cannot access temp0 again in last line. Here, reorder tries to lift temp0 just above the move occurs. However, the Rust compiler rejects this code again. Let's try next strategy. The last strategy is lattice-based weaken. This strategy tries to use an operation less likely to cause a violation. For the example, this line moves the value in temp0, but this line moves temp0 again, which is forbidden by Rust. Weaken tries to replace temp0 with multiple reference, since it is less likely to cause a violation than move. In the patch, the code is accepted by Rust compiler, so the fixing loop is finished. We implemented Rust-lancet with Rust-C version 1.679. For experimental settings, we evaluated 116 violations from 2 sources, Rust test case and juice work. We chose 4 as the maximum iteration number of the fixing loop. We have 4 research questions. The first one is effectiveness. How many violations can Rust-lancet fix? The second one is advancement. Is Rust-lancet better than baseline techniques? The third one is necessity. How does each component of Rust-lancet contribute? The fourth one is comparison with experts. Is Rust-lancet better than Rust experts? Rust-lancet fixes 102 violations out of 116 cases. The average patch size of Rust-lancet is 2.25 lines of code, and the average analyze time is 5.31 seconds. Rust-lancet patches more violations and reporting less false positive than other baseline. We compare Rust-lancet under 5 different settings. The first setting enabling all components containing 3 fixing strategies and patch validation. This setting leads to the most patched cases and non-false positive. The other settings disable each of the components. In terms of overall effectiveness, reorder stands out as the most impactful fixing strategy. Its absence results in a significant reduction in fixing capability. When behavior preservation validation is disabled, Rust-lancet still fixes the same number of errors but introduces 2 incorrect patches. Let me conclude this talk. We built an effective tool to patch Rust compiler errors due to violating ownership rules. In the future, we plan to extend it to cover more types of violations. Thanks for your listening. Welcome to scan the QR code to visit the website of Rust-lancet.